In the morning session, we had looked at rigid body dynamics from the perspective of translations, and we introduced the concept of translational momentum. Now we will get into the rotation, and that will involve the angular momentum. And you will see also that we introduced what is known as Euler's first law as part of rigid body translation. We will introduce Euler's second law as part of rigid body rotation. And for those of you who would like to check out, we are in section 2.6 for that. We've been going on and off since, as I said, I'm not following your textbook, so the order in which I'm covering the topics looks random from the textbook perspective, but I'm trying to develop it in a way in which it is, I feel, more continuous, so that for the learning process, for pedagogical purposes, I think this is much smoother learning curve. Okay, so remember we introduced Tm, which is the translational momentum, and we said it's a vector, so is angular momentum. So we will see what it is. Now that we have introduced translational momentum already, it just becomes the moment of that momentum. Okay, so angular momentum is nothing but the moment of translational momentum, and when we say moment of something, it's essentially talking about an r cross. So essentially a position vector crossed with that vector becomes the moment of that vector. So even what we normally call just as a moment is, as opposed to a force, is nothing but the moment of a force, which is essentially r cross f. So if you have no moment arm, for example, your r will go to 0, or your r cross f will be such that the cross product will give rise to a 0, and therefore you will not have any moment due to that. Something similar to that, here instead of moment of forces, we are talking of moment of the translational momentum, and we call it the angular momentum. Now, as far as translational momentum is concerned, remember that it's just the mass times the velocity for a particle, and as far as the rigid body is concerned, it's the mass of the entire rigid body times the velocity of its center of mass, which is what we derived in the morning session. So to look at it from that perspective as the total mass, it's something which is a characteristic of that rigid body, and velocity is something having a particular value for that body at a given instant of time. The center of mass has it. So both are essentially characteristic of the body at a given point in time. On the other hand, the angular momentum is not only involving the translational momentum, but also an r cross that. So that r depends on where I'm taking that position vector from. So it's not something that is unique or identified with the body even at a given instant of time. So translational momentum also is not something that's going to be necessarily constant for a body. It can vary from time to time, because velocity can vary from time to time, or even for that matter, mass can vary in the case of aircraft, etc. But at least it depends on things which are associated directly with the body, namely the mass of the body and the velocity of its center of mass. On the other hand, the angular momentum is associated with the same two quantities, because translational momentum is involved, but in addition, it's also involving a separate point about which we are going to take the moment to get to the angular momentum. So angular momentum is not something which is associated necessarily with the body. It's also associated with a particular point that you are choosing. Okay, so this is what I'm just explained. So it depends on the point about which that moment is taken, because that position vector that you're going to use in order to take the cross product, it depends on the specific choice of the point. So for example, for a particle, if you choose the point about which you want to take the moment as an arbitrary point P, then that for that particular particle, it would be angular momentum, which we, as I said, introduce the notation uppercase h, and of whichever point it is, that is the pi, of whichever particle it is we are looking at for that ith particle, pi. So that is r pi cross mi vi, but this hpi, remember, now depends upon where I am taking that position vector to the pith particle from. I could take it from an inertially fixed point, let's say O, in an inertial frame of reference I, or I could take it from even a body fixed point, another body fixed point, and calculate this. So it all depends on that choice of point, and I have to make clear with respect to which point I'm taking that moment in order to arrive at the angular momentum. As far as what you're taking the moment of, very clear, because we already said it's of the translational momentum Tm, and that is nothing but the mass times the velocity of that particular particle, which is m, the ith particle, and therefore mass is mi and the velocity is vi with respect to an inertial frame of reference. Okay. Now to extend this to the set of particles, because our eventual goal is to go to the rigid body, so we use the same approach which we did in translational momentum, and in understanding the translation of the rigid body, we started with a single particle, then we went to a set of particles, no conditions applied on the set of particles, then we brought in the rigid body as a special case of the set of particles, and then we derived the equations for that. Instead of summations, we got in integrations. Instead of mi's, we got rho dv's, etc. Right? We'll do the same thing over here. So now, first thing is we want to go from one particle to a set of particles, which means a summation. That summation is over I is equal to 1 to n, where n is the total number of particles in that particular system, right? So once again, it's the position vector of each and every one of those particles multiplied by its corresponding mass times the velocity of that particle in an inertial frame of reference. And therefore, since all of this is with respect to a particular point P that we have chosen, we put that subscript P over here. Okay. So here also, in fact, the appropriate notation for this should have been H subscript P, and maybe I could have put a Pi on top to refer to the fact that it is for the ith particle, whereas this is for the total system. Okay. So usually whatever we put as a subscript is the point about which we take the angular momentum. So this is not an appropriate way of stating this. This is just to say that it's of the ith particle we are doing it, but actually, truly speaking, it is also HP, but for the we can say within brackets for the p ith particle, or the one with the mass mi and velocity vi. Okay. So now it's very clear that if it's this for the ith particle, all that you have to do is to sum over the n particles, and they get the angular momentum for about p for the same system. Now the angular momentum about any point P, which is related to is always related to angular momentum about any other point. And in particular, we are interested in a specific point that we introduced in the morning called the center of mass, which we denoted by C. So typically we would have already calculated the angular momentum about the center of mass. So if we want the angular momentum about any other point, instead of going to the fundamental definition and then trying to each and every time calculate this summation, we can actually use this particular expression to get to the angular momentum about any other point with respect to from the angular momentum that we already have for C by just adding an R cross L. Why is that so? Because you know that the position vector in going from O to P can be thought of as going from O to C and then from C to P. Okay, so you can see that the position vector is additive because it's a vector addition. Going from, instead of going directly from O to P, I can go via C. Okay, which is what this essentially takes care of with the appropriate signs and the algebra that is involved, and therefore we can get the angular momentum about any arbitrary point P if we know the angular momentum about C without having to go to this definition, which is kind of monotonous in terms of actually calculating point by point. Okay, we just have to add for the overall system what is the translational momentum. We have to just take the cross product, pre-cross product with the position vector of P with respect to C. So now we get to what is known as Euler's second law. It's equivalent of the first law that we saw in the morning. First law is valid for translation. Now the second law is valid for rotation. First law involved translational momentum L. Now the second law will involve the angular momentum H. So Newton's second law for the ith particle is a starting point for us for each and everything that we are doing. We are starting from the basics, which is for the ith particle, what is all the forces that are acting on it, that should be equal to its mass times the acceleration, right? So all the forces which are acting on it can be divided into two parts, like we saw in the morning. One is coming from those which are outside the system itself, entire system, and the others which are coming from within the system, one particle acting on the other. In particular, we are looking at the ith particle, and therefore it's a summation over j of small fij. All the other particles, what is the force that they are exerting on the ith particle, we sum it over in a vectorial manner algebraically, and then we get the total resultant force acting on the ith particle. That should obviously be equal to the mass of that ith particle times its acceleration with respect to an inertial frame of reference, which is ai. Now we take the moment of this equation because we want to get to angular momentum. So we just have a pre-cross product of all the three terms that we have on the first equation with rpi, which is the position vector to that particle pi from some point, and that point is the point p, because then the angular momentum that we will come up with is about that particular point p. Okay, so there's no specific choice we are making about p, no conditions involved. It could be any point whatsoever. So this particular equation is valid because the first equation is valid. All that we are doing is to take the pre-cross product with rpi. So when we do that, we can do a few simplifications, just like what we did in the previous class for translational momentum. We were doing that for angular momentum over here. The first thing we wanted to do was to simplify the left hand side, and we wanted to take advantage of the reciprocity principle, which is a universal principle which we said that whenever there's a double summation of fij over I and j both summed over n, 1 to n, then that has to go to 0 because every action has an equal and opposite reaction. Newton's third law kicks in, so the second term will vanish and we will be left only with the first term, but we'll have to have a summation over I equal to 1 to n. The right hand side, on the other hand, as of now remains the same, except that there is a summation that has come up over I equal to 1 to n, giving the cross product of the position vector of each particle times its translational it's the mass times the acceleration. Still we have not yet gone to the translational momentum, right? So now there also, if you remember, we first simplified the left hand side using Newton's third law, then we went on to simplify the right hand side, which is the same thing we will do now. We have already simplified the left hand side, dropped one term because of Newton's third law. Only one term remains on the left hand side. Now we want to simplify the right hand side by introducing the concept of angular momentum, which we already did in the previous slide. We want to invoke that into this equation. So the left hand side is nothing but, if you see, the cross product of a position vector times the force, which is nothing but the moment about that point. Okay, so about which point? About the point from which these position vectors are measured. Remember, these are position vectors to the ith point from P, which is an arbitrary point that we chose from. So it is from P to Pi. Okay, so therefore all these moments are about that point P, whose position vector we have used to take the pre-cross product of the forces Fi. Okay. Now again, of course, the summation remains because it's the sum of all the moments, because there are multiple forces, external forces acting, and all of them can in general contribute towards the moment. Okay. Still the right hand side remains the same. We have been so far able to only simplify the left hand side. We want to see how we can handle the right hand side. The right hand side is related to, just like in the previous case, the right hand side was related to the translational momentum. In this case, it's related to the angular momentum. You would be tempted to say yes, but it is conditional over here. It's yes only for a specific type, or rather I would say two specific types of the point P. Can anybody guess for which kinds of points this equation might be valid? I am not going to ask you for the proof, but just what your guess is. So whereas this same thing, when we wanted to relate it to translational momentum in the previous case without the cross product with R, it was always related to translational momentum, no conditions. Okay, period. It was the case. But here it's not always related to the angular momentum. It is related to angular momentum if and only if P is selected in a particular way or in two particular ways. Okay, can you guess which choices of P could probably make?
Does P have to be at the center of the mass?
Good, yeah. So that's one special point that we introduced in the morning. So it's a good guess that that could be a point about which the right hand side could become related to the angular momentum about the center of mass. Any other point you think? There's a second category of point. Center of mass is only one value, one particular position that we are interested in. But as far as the other category is concerned, you get a little more liberty. You can start using this equation with angular momentum for a few more cases. Any guesses on what the other kind of points could be? Yeah.
You briefly mentioned center of gravity. Would that at all come into play with this equation?
Yeah, it's a good point. In problems where gravity is involved, that would be an appropriate choice because that's the only force which is causing the moments, then that would be it. But it's kind of an extension of the center of mass concept, just that it's a little more complicated problem. But there is another class of points, not just a point, but a class of points for which we could still relate the right hand side to an angular momentum.
Could it be that the point has to be on the body or within the body?
Not necessarily. Whether it's on the body, which is a boundary point, or internally, there's not too much of a difference in terms of this particular thing, that is mass, velocities, angular momentum, etc. Only the actual position matters. Doesn't care whether it's a boundary point or not. Because remember that we have gotten rid of this already. So it's only this where the interaction terms for the boundary points is little lesser because it's only one part of the boundary which is involving that. Now that we have got rid of that, only we're dealing with external moments. It really doesn't matter because the external moments we're talking about now are not for individual infinitesimal masses, but for the whole thing. Okay? And again, we have not yet gone to rigid body. We are still talking of system of particles. Okay. In fact, that particular kind of point opens up a huge way in which we can utilize angular momentum. If not for that, maybe angular momentum would not have become such a popular concept at all. People wouldn't have utilized that because always to get it towards the center of mass is kind of challenging. But once we have that point, things become a little more broader in application. Yes, radius of gyration is a fallout of something that we will introduce as a concept. Now we are talking of a class of points for which this could be valid. Yes, yes.
Would it be like a different reference or not?
Yeah, can you qualify that? What kind of reference frame?
Well, because if you're thinking about like an aircraft or in relation to like Earth, like those would be different, so you have different center of masses, but I'm trying to think of
Yeah. So already Daniel has said one type of reference frame, which is the body itself. Like, and I said no to that, right? So what other reference frames have we been talking about very frequently? Yeah. Yeah. So any point fixed on an inertial frame of reference, you can actually get your right hand side to relate to your angular momentum, and that's the power of this particular concept. Okay, so which is why angular momentum has become so popular in a lot of dynamics derivations. So let's see, of course, why it is so in the next few slides. Okay, so that's the second category of points we'll go to first. We'll go to Daniel's point, which is the center of mass, later. So right now, let's choose a particular point. Let's say we will use this common notation unless otherwise mentioned. We will talk about an arbitrary point as P. We will talk about an inertially fixed point as O. We will talk about, let's say, each particle as Pi, and if it's part of a continuous rigid body, then we will call it as Q. So we will use some of these notations unless and otherwise mentioned, so that we don't confuse with too many different variables for the same kind of points. Okay. So now Euler's second law in terms of angular momentum is what we want to get. but this time angular momentum always, as you know, is not only a property of the body, but also of at a given time, but also of the point that you choose. And here we choose a point which is fixed in any inertial frame of reference. Okay, doesn't matter. So any inertial frame of reference. So now what do we want to eventually get to? We have already simplified the left hand side and shown that it's equal to the resultant moment that is acting about a particular point P which you have chosen. And then we want to show that this right hand side is kind of related to the angular momentum, which is what is the purpose of this particular slide. Okay, so if you take the moment about any point O which is fixed in an inertial frame of reference, then you see that that particular angular momentum, whatever general expression that we had, which we had as HP, now becomes H about O, right? So just replacing P with O, and then your right hand side therefore becomes the position vector from O, for which we have been using a specific notation, which is uppercase R for the ith particle, which is R subscript I, right? So that crossed with the mass times the velocity of that particular particle. Okay. Now, if you want to look at the rate of change of this angular momentum and you want to compare it with the right hand side over here, so let's start with this and see d by dt of the left hand side, which is the angular momentum about the inertially fixed point O, then becomes, because I can interchange the d by dt and the summation, remember that we can do it in either order, doesn't matter. So we take the d by dt into the summation term by term, and then therefore since we have a product, we have to take one by one, which means that we use the product rule, like uv, if you want to take the derivative, it is u dv plus v du. So first let's take the derivative of Ri, and all these derivatives, unless otherwise mentioned, are with respect to inertial frame of reference, in the same inertial frame of reference in which O is fixed as well, for example. So then d by dt of Ri, and keep the second term as it is. Now keep Ri as it is and take the d by dt of the second term, and if mass is not varying, mass comes out and it's just a dv by dt that we have. Okay, this is quite straightforward. Now if you look at this, we see that dh naught by dt can now therefore be written as, if you look at the first term, I think I'm interchanging this, right? No, I'm keeping it as it is. So what I've done is I put my dvi by dt as acceleration, ai over here, keeping the rest of the second terms as it is. Now I'm recognizing that the rate of change of the position vector from an inertially fixed point O to the pith point is nothing but its velocity, right? So in the inertial frame of reference, so I'm just bringing in vi over there, right? So I'm bringing in vi over there. So it's very clear that all that I have done is to recognize dr by dt as a velocity and dv by dt as an acceleration. That's all the change I'm making going from this equation to this. Left hand side remains the same, only in the right hand side I made that change. Okay. Now the first term drops off. Can anybody say why? Yeah.
Because vi cross vi.
Exactly. So any vector crossed with itself should go to 0 because they are parallel to each other. Mi just being a scalar multiplying factor, you can take it out, and so it's just vi cross vi. So the first term drops out, you have only the second term. So this is a huge advantage that we are getting, that there's a huge simplification coming in. Even though we had the derivative of a product and we had to kick in the product rule and get two terms, one of them actually drops off because the definition dri by dt is vi. So here is where we are utilizing the fact that it is not any point, but any point which is fixed in an inertial frame of reference. If it was not an inertial frame of reference, remember, then this would not have been vi, and therefore this would not have gone to 0. So that's the advantage that we are getting now, so that only the second term is retained, which is what we have over here. And now that's if and only if. So many of you might be familiar with this usage of this term. IFF essentially means if and only if. Okay, so that's if and only if the point O is fixed in an inertial frame of reference, then Euler's second law will take this particular form. Okay, so from the previous slide we had this MP is equal to RPI cross MI AI, which is nothing but we see is exactly what we have on the right hand side over here. So now the right hand side can be simplified to nothing but the moment about that particular point. So this is for a generic point P, whereas now we have about the specific point which is inertially fixed. So instead of P, we are going to use O in this general formula, and therefore replace this right hand side wherever P is there with O, and therefore we are going to get the sum of all the moments that are going to act on the system of particles from external sources. That resultant should be equal to the time rate of change in an inertial frame of reference of the angular momentum about the same inertially fixed point. Okay, so this is a very simple formula, m naught equal to dh naught by dt or h naught dot, but you should understand all of the implications and the meaning of the specific choices that we have made, that O is an inertially fixed point. For any other point which is not inertially fixed, this will not be valid, because you'll have an additional term that you have to live with, which is essentially this particular term. Okay, so is this very clear? So why that particular choice, kind of choice rather, because it's not a single choice. It's because there are so many points which are fixed in an inertial frame of reference, and there are so many choices for inertial frames of reference, approximate of course, but nonetheless you have a huge bunch of points that you can depend upon to use the fact, just like we were saying, forces are the time rate of change of translational momentum, which was Newton's first law, Euler's first law. Here we are having the moment which is applied about any inertially fixed point is equal to the time rate of change of the angular momentum about the same point for the same system of particles. Is this clear? Any doubts, questions? Okay. So now the second point, in fact the first, because Daniel mentioned that first before Gracie did. So that's the center of mass, right? And if you look at the final equation that I'm going to get, here it is O over here, m and h d by dt. If you look at the next slide, what I have exact same equation. I only replaced O by c, right? So in other words, the same equation, that the time rate of change of angular momentum equal to moment, is applicable not only for inertially fixed points but also about the center of mass. Of course, you have to take both the moment as well as the angular momentum about that center of mass. Okay, so now let's see how this works. What is the reason behind this holding true? Okay, so you've not derived it yet. We are trying to get to that. Okay, so now Euler's second law for the angular momentum about O, which we got in the previous slide, we already saw, is nothing but the sum of the moments about O is equal to the time rate of change of the angular momentum about the same point O, which is inertially fixed. Next is that the angular momentums about C and O are related. In fact, we said that if we knew the angular momentum about C, we can get angular momentum about any point P. Okay, so now instead of P, we are going to use a particular point O. So if you can get HO in terms of HC by using the same relationship, which was just obtained by the fact that you can get to from one point to another point via yet another point, and therefore a sum of two position vectors to reach to a different point. So which is all that we are taking here, just that we are specializing. Instead of P, we are using O. This is an equation that we have already derived earlier. So now applied moments about the center of mass and about O are also related. So this is one thing we are keeping aside for the right hand side to simplify the right hand side. To simplify the left hand side, we are trying to look at m naught. Something similar to that is valid here also, that if you want to take moment about one point, you can take it about any other point, and then you use the position vector from one point to another point and cross it not with angular momentum now but with force, because force and moment are related in the same way that translational momentum and angular momentum are related. Remember, moment or torque is defined as a cross product of the position vector with the force, whereas the angular momentum is defined as a cross product of the position vector with translational momentum. Okay, so same, you see the parallel between these two. It's the same kind of equation, but we are using for two different quantities. One is for angular momentum, the other is for the torques or the moments. So now that we have these, we can go back and substitute in that. Thus, you can see that if and only if that point C happens to be the center of mass, then the Euler's second law holds that mc is equal to d by dt of hc. Do you have any questions or doubts about this? How we get to this equation from those two? Yeah? Okay, now we like to look at a few more forms of the angular momentum, or rather Euler's second law we put in an angular momentum form, and this is what you remember we had for the two specific kinds of points, namely the center of mass and the inertially fixed point. Center of mass we denoted by C, and inertially fixed point we denoted by O. We say any arbitrary point, if it is there, P, which is not necessarily the center of mass or the inertially fixed point. If you have any other point, then you will not in general have it as d by dt of the angular momentum. Okay, so this is not true. It is in fact equal to this, but this cannot be simplified to this particular form. It can be simplified only for those two kinds of points. One is the center of mass of the same system of particles, the other is an inertially fixed point. And when you have simple rotations, for example, what Daniel said later on becomes valid, that if you have a point which is fixed on the body, but if it happens to be an axis of rotation, so then it's fixed both in the body as well as the inertial frame. Therefore, since it is also fixed in the inertial frame, therefore that becomes a right candidate to use this particular thing, but not for any other point on the rigid body. Okay, so other than the center of mass and the axis of rotation. Okay, so now this is in terms of arbitrary points is complicated. So let's see why. Euler's second law is simpler for a particle set or rigid body in terms of the angular momentum about 2 points that we have already seen. One is the point which is fixed in an inertial frame of reference, and we always use O to denote that. We remember we always used to draw those three axes, x, y, z, I hat, j hat, k hat, denoted by I with a circle around that, and then we used to call the origin as O, right? So it's some point which is fixed in an inertial frame of reference. Whenever you have such a point, you can take the moment of the forces about that, you can take the angular momentum, and you see the both are related to each other by just the derivative with respect to time. So that's what we had. The other, of course, was for the center of mass of the same system of particles, a similar kind of an equation. All that we are doing is replace O with C. In the previous two slides, we have seen the derivation of these two equations. Oops. Yeah, I think I covered that. So it's only for those 2 points that this simple form is valid. For the arbitrary point P, it is not. Then there is something about conservation, and this is something that you come across in pretty much every branch of physics. You have conservation of energy, conservation of mass, conservation of momentum, and here we are talking of conservation of either translational momentum or angular momentum. In this slide, we are looking at conservation of angular momentum. When do you think angular momentum will be conserved? In other words, as the system of particles moves, not necessarily together in the same way, the particles could be moving with respect to each other also, and as a whole the system might be moving and rotating as well. When you are having all these kinds of things, under what condition do you think that the angular momentum will be conserved? What does it mean, conserved? It means that it doesn't change with time. Okay, it could be not necessarily conserved over the entire period of time, maybe a certain sub period for which the angular momentum is conserved. Yeah, anybody?
As far as the inertial, like in the case of flywheel, the angular momentum is conserved. It's on the angular momentum is conserved in the case of a flywheel.
In the case of what?
Flywheel.
Flywheel.
Flywheel. Like the governor and a flywheel.
Oh, okay, flywheel. Okay, okay. All right, right, right. Okay, okay.
So their angular momentum is conserved.
Okay, okay. Okay, that's a good example, but I'm looking at not examples, but under what conditions will the angular momentum be conserved? Yes, like.
If there's no external forces being applied,
Exactly. What will be conserved then?
momentum,
Which momentum?
linear momentum.
Yeah, translational, which we call as translational, right? But now we are talking of conservation of angular momentum. So you are heading in the right direction.
So no moment.
Exactly,
Okay.
exactly. So these are the two conditions. When there are no forces, translational momentum is conserved, because remember that we have said that the total forces is equal to dl by dt. So if dl by dt has to be 0 for conservation, L has to be constant. Therefore, your forces have to be 0. Similarly, angular momentum we have already shown, at least h0 and hc are such that, their time derivatives are equal to m0 and mc, right? So if m0 and mc are 0, then you will see that dh0 by dt or dhc by dt are 0, which means h0 or hc are constant, right? So that's the case. So it's very counterintuitive also when you're looking at continuity equation, for example, in fluid mechanics. Essentially you're saying mass is conserved, right? So it means that there's no transfer of mass between the system and out of it, right? Or if there is some transfer, then whatever gets in gets out as well. So essentially over the same period of time, that's essentially what you're talking about. Energy, when you're saying energy is conserved, essentially what you're meaning is that there is no loss of energy in the motion, let's say like because of friction or whatever the kinds of dissipations that could arise. Essentially you're saying that therefore the system's energy is conserved. But this is far more restrictive, because no forces are allowed. Then only translational momentum is conserved. No moments are allowed, only then angular momentum is conserved. So it's far more stringent, in the sense that it's essentially going back to Newton's first law. What is Newton's first law saying? That a body continues to remain in its state of rest or of uniform motion if no external forces are acting on it. Same thing here, you're converting that to, for a set of particles, no moment being there, and therefore your angular momentum is conserved, doesn't change. Okay, so if the applied moment equal to 0 about point O, so these are for specific points, remember, it's not for any arbitrary point. So for a point O, which is an inertially fixed point in an inertial frame I, then you get d by dt of h naught equal to 0, which means h naught is a constant, okay? For a rigid body, so to give some examples, the flywheel was a great example, but simpler examples would be, for a rigid body, it could just be a pivot point which is fixed in both the inertial frame of reference as well as the rigid body, and it need not necessarily be the center of mass. For example, if it's a rotation about a fixed axis not passing through the center of mass, then you essentially have that kind of a situation, okay, where essentially like you could think of a flag mast or a flag pole onto which the flag is attached. So you can think of that flag mast being attached to the ground, the earth as an inertial frame of reference, but it's also part of the flag, a certain part of the flag which is fixed to it, right? So something like that. So you see that you would have a situation like that. The other, of course, other than inertially fixed point, was the center of mass that we dealt with. And so there also, if that point P happens to be C, then d by dt of hc will be equal to 0 if there are no moments acting about C. So this is if no moments are acting about O. This is if no moments are acting about C, okay? Resultant, or in other words, there are moments, but they cancel each other out, okay? Some are positive, some are negative, and therefore the total sum becomes 0, vector sum, of course. So along all the three directions I, j, k hats, it all goes to 0. Then you would have h naught or hc being constants. Okay, so these two angular momentums, however, are related, as we saw. In fact, angular momentum about any 2 points for a given system at a given instant of time are related through this sum of a cross product of the position of between those 2 points with the translational momentum L, and therefore these two are holding as well. So if one of them is true, then one of them goes to 0. The other can be evaluated using this particular equation just by using a cross product of R cross L, okay? So no moment means either no force. See, because that's one way in which you can avoid moments, because see, both of these, that is the conservation of h naught or hc, is valid only under this condition that there's no applied moment. But how can you have no applied moment? One case is when there is no force, because if there's no force, there's no moment, right? Because it's the force is the source of the moment about when it has a certain moment arm. which other situations can you have no moment? When you have a force, but you can still have zero momentum. What is that situation?
Momentum being
Exactly. So the force is passing through the point about which we are taking the moment, right? So it could be either an inertially fixed point or through the center of mass. If the force itself or the resultant force of all the forces is passing through that point, then obviously you can have zero. Any other situation? One is if forces are zero, one is if r is zero, right? So because remember, the moment is nothing but r cross f, right? The position vector crossed with the force, right? So you have seen two examples. One is if f equal to 0, other is r equal to 0, okay? Then r cross f can be 0. But there's a third category where r cross f can be 0.
R and F are in the same direction.
Exactly. They are parallel to each other or in the same direction. Then obviously you can still have r and f both non-zero, but r cross f will become 0. In that case also, your angular momentum is conserved because moment is 0. So the force passes through a point about which the moment is taken, which is the case which the group captain pointed out, which is essentially when your r equal to 0. The third, of course, is when they are both parallel to each other. So conservation of angular momentum in inertial frame of reference or with respect to the center of mass under these conditions. Okay, so now we are done with a major part of your book. Pretty much, I think 1, 2, and 3 three chapters, whatever is there, we have already covered. Now we can get into certain important parts of chapter 4, which is talking about Euler's second law, which we just introduced, but using a new concept. We already introduced one concept, which is the angular momentum, which we denoted by h. Now we want to introduce another quantity, which we will denote by I with some subscripts and superscripts, and that is nothing but the mass moment of inertia. Okay, so the mass moment of inertia, many a times just called as moment of inertia, because you know that you're dealing with dynamics, therefore you assume that it's mass moment of inertia, but the right way of calling it, to be more precise, to avoid confusion with other moments of inertia like area moment of inertia, etc., is better to call it as mass moment of inertia, right? So this is covered in 2 of the sections in your textbook if you would like to take a look. So coming to the first thing that we want to derive over here, we want to show the very simple relationship for your angular momentum about the center of mass involving 2 cross products, okay? And in fact only 2 variables, namely r and omega. And something very similar to this, if you remember, we had seen when we introduced the centripetal acceleration, just that there were 2 omegas there and only 1 r. Here there are 2 r's and only 1 omega, okay? But there we were talking about an acceleration, okay? Centripetal acceleration. Here we are talking about an angular momentum about c, okay? But in structure, somewhat similar, there are certain similarities that you will utilize, okay? Just a few minutes back, Nafis mentioned that if you have a cross product of the 2 similar vectors, you would have it as 0. You have RCQ and RCQ here. Will this cross product go to 0?
because it is crossed with
Yeah.
first and then thereafter.
Exactly. So because it's crossed with omega and there's no bracket, I can either take this cross product first or this cross product first, doesn't matter, right? So if I take this cross product, already the cross product will be perpendicular to both of those. So it will definitely be perpendicular to RCQ, and then only I'm taking a cross product with RCQ, and therefore it will be in general non-zero, okay? So this is what we want to get to, this simplified form, but we are not yet there. We have to show that, okay? So this is the purpose of this particular slide, where we want to get the expression for the angular momentum about the center of mass for any rigid body, okay? How do we go about doing that? So now we have, for the particle set, you have the angular momentum about the center of mass, which we have already derived in the previous slide. We have said that it's equal to RCI cross MIVI. So what is in green font is something that we have already derived in a previous slide. What is the red font is what we want to get to. In between, we will use yellow font or orange font to show how we get through that particular process, okay? So the other thing that we had is that, okay, for a rigid body, the angular momentum about the center of mass is equal to RCQ cross VQ. So in other words, we are saying that this particular thing can be specialized to any point, which is because we want to go from till the previous slide we had system of particles. Now we are getting into a new thing, which is this rigid bodies. Okay, we're getting into the rigid bodies over there. So that rigid body that we are dealing with right now will require, just like in the translational momentum in the morning, remember, when we wanted to move from a system of particles to the translational momentum, what we did is we replaced a lot of things for the system of particles to the rigid body. When we wanted to do that, we replaced the summations with integrations. We replaced the mi, the particle mass, with dm, infinitesimal mass, and dm in turn we replaced with rho dv, and the integrations were all volume integrals, therefore instead of summations over a finite set of particles. Okay, so that's the same approach that we will take over here. So it's very similar to what we did for system of particles, just that instead we have integrations and dm's instead of mi's. Okay, now so remember that this particular thing we already had for the system of particles. Instead of dm we just had mi over there, and instead of an integral we had a summation. That's all that we are doing, to replace those summations with integrals and the mi's with dm. Okay, so once we do that, we have this RCQ cross VQ dm, because remember this is nothing but translational momentum of that infinitesimal mass. And so you're taking r cross the translational momentum, you should get the angular momentum. When you integrate over the entire thing, you get for the whole rigid body instead of that just infinitesimal mass. Okay, so where q is a notation that we will continue to use in the next few slides for any point at the center of that infinitesimal mass dm, because anyway we are going to shrink that to 0. So essentially it means that it is that particular thing, like what we are talking about as a particle, now we are talking about as an infinitesimal mass, and it is at its center that we are looking at. It could be on the rigid body, in the rigid body, wherever we're essentially making up the material part of the rigid body. Okay, now this is something that you have used pretty much for every problem that you have solved in your homeworks. You want the velocity of one point with respect to another. We used, of course, P and Q there. Instead of P, I'm putting C over here to bring in the center of mass, and Q, I'm giving a specific meaning over here that it is in the middle of the infinitesimal mass. So now, because this equation is valid for any 2 points which are fixed on the rigid body, these 2 points are fixed on the rigid body, which is the center of mass and the what you call as the infinitesimal mass, one particular material point that you're tracking, and their velocities are related by just this particular cross product, which involves the angular velocity of that body on which C and Q are fixed with respect to an inertial frame. So if C and Q are fixed on a body B, then this should actually be written as pre-superscript I and here subscript B. So it's omega of B with respect to I, that is the omega we are talking about. Since there is only one body and there's only one inertial frame we are dealing with, we are taking that as a default and just calling it as omega, right? And of course it has to be from the known point at which information is known to the point at which information is not known, to which we want to get to. So it's from C to Q. Okay, so now therefore and this is very different from some of the terms that we have been using in the previous slides, where we were just breaking up the position vector going from one point to another point via another point. We were adding the position vectors. This didn't come from that kind of a thing, remember. So that's why it has this form, whereas in the equations that you would see in the rest of the slides this afternoon, this was kind of interchanged. Okay, so they are coming from two different sources. You might recollect we have derived this also in a much earlier class, whereas the other one is a straightforward thing going from one point to a third point through a second point, and therefore the position vectors are getting added up. So don't get confused. In some cases it's CQ, and some cases it is QC. The source of the derivation itself is different. Okay, so therefore now that we have VQ, so this VQ can be substituted over here. Okay, so this expression for VQ can be substituted there. Obviously you have two terms because you have something plus something that goes in over here. Both of them should have a pre-cross product with RCQ. So that's what you see over here. Okay. Now out of this two terms, in general, one will drop out. Why? So you can see the final expression I have here. So it's very clear that the second term remains. Okay. It's only the first term drops out. That is RCQ cross VC DM is dropping off, right? Why is it 0? We already said many ways in which a cross product can go to 0. Either this is 0 or this is 0 or both are parallel to each other. Does any one of these conditions hold in this case? Is RCQ always 0? What is RCQ? C is the center of mass. Q is any arbitrary point, material point on the body. Okay, and you have an arbitrarily shaped body, so your CQ will be running in all kinds of different directions, and it's definitely not 0, right? Unless the rigid body is a point or a particle. We are going back to that singularity, right? So in general, your RCQ is not 0. Okay, what about VC? Because even though we are studying rotations right now, I'll come to you. Even though we are studying rotations right now, we know that the rigid body can have translation as well simultaneously. So the center of mass can be moving with a certain non-zero velocity. So VC is also not 0. So is it that these two are parallel to each other?
Oh, I was going to say that if the frame of reference is, okay, if the point is fixed relative to a moving frame of reference, then we could theoretically say that VC is 0, correct?
True. True. So you could have a situation where, like for example, you have, let's say, I pivot this at its center of mass, and it only is like a seesaw. Okay, so it's going like a seesaw. So in other words, its center of mass doesn't have any velocity. So it's a special case where VC can go to 0. But what I'm saying in going from here to here is a general. In general, for every body, I can drop off the first term and retain only the second term. Why? So because in general bodies will have translation, so this will not go to 0. In general, rigid bodies are not particles, so this will definitely not go to 0. So the only other way in which this can go to 0 is because these are parallel to each other. Are they parallel to each other?
Yes, they are. RC is a position vector from the point of our reference to RCQ from C to Q.
Yeah.
It is pointing in that direction.
Okay.
Velocity is also, it's an angular velocity. AM is rotational, whereas this VC is not. This is the translational velocity, which is in the direction of R. Actually.
Okay. See, this VC is the velocity of the center of mass.
Yes.
Okay. Whereas RCQ is from the center of mass to any arbitrary point, and RCQ will be in multiple directions for different Qs. So for one particular Q, it might be right that VC and RCQ are parallel to each other. But Q are an infinite set of points, and each point will have a different RCQ. So can ever RCQ and VC be parallel? No. Only very, very special cases it might be parallel. Most of the points it will not be.
Is it that no matter which point that you pick as Q, like if you're taking one specific Q, no matter what point you pick, is it that VC, like the center of mass, will always be moving towards Q? Like that's why you're picking the point, right? You're multiplying, like you're finding R from C to Q because the motion is towards Q, right? Not
necessary. See, Q is any point on the body. What we are trying to get to is knowing the particle kinetics and particle kinematics. We want to get to the rigid body kinetics or kinematics. So we are just considering the body to be a set of points, okay? And each of those points is an eligible Q, okay? And we have to consider each and every one of them. We cannot leave out any point, okay? So RCQ has many different values, infinite number of values, infinite number of directions, infinite number of magnitudes, okay? So there's no way it can go to 0, neither can it be parallel to this. But still I'm saying this is a general thing that I can drop off the first term. Why? Yeah.
I'm not sure exactly how to explain this, but I think what's happening is sum of those terms over the entire body, they cancel out.
Yeah.
Because something to do with how momentum.
Yeah, so I'm glad you brought that word sum, but instead of sum, what we are doing, because it's a continuum, we are doing an integration. So now I'm not saying that RCQ into V cross VC is 0. I'm saying integral of RCQ cross VC dm equal to 0. Why?
It's because it's like you're doing it from the center of the mass. So won't it end up being like symmetrical in some way where as you go to each point Q, eventually they'll all cancel out?
Okay, that will be true, for example, if you have a axisymmetric or a doubly symmetric kind of a cross section, when you have two planes of symmetry like a cube or a, let's say, a sphere or something like that, right? But this is generally true for any arbitrarily shaped body. So there's no point to cancel each other out. So for each and every Q, there may not even exist another point over there at a minus location, right? So in terms of the position vectors. So why does this happen? But Daniel is getting in the right direction. Yes, this is not 0, this is not 0. These two are not necessarily parallel to each other. Therefore, RCQ cross VC is not necessarily 0. But once the integral and dm comes in, it does go to 0. Can you think a little more on why it happens? First of all, in that integration, which are the things that are constant and can be moved out of the integral? Is this something that can be moved out of the integral? No, because it involves Q, the material points, and you have to sum across all those material points in this integration, so that cannot be moved out. What about VC? Yeah?
To be a constant.
Because VC doesn't depend on Q, okay? VC is the velocity of the center of mass, and therefore it's not necessary for it to be within the integral. So I can integrate RCQ dm and then cross it with VC, okay? Instead of having to take the cross product and then integrate, I can first integrate RCQ dm and then take the cross product with VC. Now, are you seeing some light at the end of the tunnel?
I'm just trying to think about what the integral of all of the positions of the points relative to the center is.
So that's what integral RCQ dm is.
Yes.
Yeah.
It's mass moment of inertia.
Hmm?
This is the mass moment of inertia of the body.
Mass moment of inertia.
RCQ dm, integral of RCQ dm. Is you are taking a point and then that
Yeah.
inertial moment that
Right.
is going to
So it's the first moment of the mass.
first moment of the mass.
It's not the inertia, which is second moment. It's the first moment because only one R is involved.
Correct.
But it's not about any arbitrary point. It's a particular point that we are looking at now. Which point? Which point are we looking at over here? See, Q is the one over which the integration is taking place, but the other point is fixed. That's the center of mass. And integral RCQ dm equal to 0 is how we defined the center of mass, if you remember in the morning. Right? That is the very basic definition of your center of mass. So if you're taking it instead of C, if you had some other point O from which you're doing, then you have to take that integration, divide by dm to get the coordinate. But if you're taking it from C itself, you will end up with 0. Right? So that's the definition of center of mass, that integral RCQ dm equal to 0, and that's always true. Okay? Which is why the first term drops off and you are left with only the second term over here. Yeah? Okay. So that's your angular momentum about the center of mass. We have a very simple expression over here now. Very similar to, as I said, the centripetal acceleration, just that instead of omega squared r, you have something like a omega r squared over here. Of course, it's oversimplifying the statement, but because there's a vector there are vectors involved and the cross products are involved and appropriate directions have to be taken. But in the simple case where you have a 2D motion where you have omega without loss of generality, I can introduce my ijk in such a way that k hat is parallel to omega, and then I will see that this can turn out to be a very, very simple expression that I can arrive at. Okay, let's move on. Yeah, So now we look at the angular momentum's expression for 2D. Okay, so it's in other words, whatever we had so far was general solutions 3D. You could have any arbitrarily shaped body extending in all three directions: I hat, j hat, k hat, x, y, z. But now we are looking at just 2D body, a rigid body, which means its angular velocity is along a specific choice amongst I, j and k. So without loss of generality, as I said, I can choose that to be k hat. Okay, and also the point about which we want to take the angular momentum, we are fixing to be the center of mass, not any arbitrary point. Okay, for this slide alone. Okay, so now coming to 2D rigid bodies, very clearly, if I'm taking the angular velocity about the k hat direction, or in other words, it's not that I already fixed ijk and then I'm trying to define the problem. So I've looked at the problem definition, and introducing the frame is the prerogative of the analyst. So I introduce it in the way that I want to make my derivation simple. Okay, doesn't matter how I introduce, I just have to be consistent with it throughout my derivation. So whenever I have a situation like this, that the angular velocity is not changing its direction, it can change its magnitude, but it's not changing its direction, then I can choose always that particular direction of the angular velocity to be k hat, which means all of the motion, which is translation, is happening in the ij frame, and in other words xy plane, and therefore the RCQ that you are going to be talking about is only in your I hat and j hat, because that's the 2D body. It's in the plane. That plane is the xy plane. Okay, so you have the position vector to any arbitrary point of the body, which is a planar body. Now talking of q, that q can be located from the center of mass of the rigid body by going a distance xc along I hat and yc along j hat, and that's it, no more, because there's no z component over there. On the other hand, omega has only a z component, which we will call as omega subscript z along k hat. Okay, so now in the previous slide, we remember that we had this expression. Now we have an expression for RCQ and we have an expression for omega. I have to just substitute for RCQ twice here at the beginning and at the end over here, and for omega over there, and take the cross products. It only involves Cartesian system, ij's case, so you know that those cross products are fairly easy to take. And when you do that, this is what you end up with. The angular momentum about the center of mass is equal to, just like the angular velocity, it also has only a k hat component, okay, which is anticipated because the rotational motion is all happening about k hat. So whether it's angular velocity, angular acceleration, angular momentum, all of these are going to be along k hat. And very interestingly, the way this breaks up, the way this breaks up is as an integral of xc squared plus yc squared over the entire body. Integration is with respect to dm, which we can replace, of course, as rho dv, and the dv can be replaced as a dA with a particular distance, because you are now only looking at that plane. So it becomes a fairly straightforward thing to do. Okay, so now you see that we introduce a new concept. Just like we introduced angular momentum, we introduce a concept which is a property of the geometry, and that just like center of mass is a property of the geometry, we introduce this particular quantity called I, and this I has a subscript zz to show that it is the product, it's the mass moment of inertia about the z direction, about a particular axis which passes through the center of mass. Okay, so that's all this symbolism essentially represents. So always you should have mentioned the axis. If these two are the same, then it is essentially a moment of inertia. If these two are different, like xy or yz, zx, etc., then it becomes what is known as a product of inertia. Once again, it's a mass product of inertia, just like this is a mass moment of inertia. But you should always also specify the point about which it is taken, through which the axis passes, and that in this case is this point C. Okay, so whatever is in this rounded brackets over here, that we are replacing. So the rest remains the same, that omega z times k hat is what we are putting over here. So we get a very, very simple relationship for the angular momentum about the center of mass for a rigid body to be its mass moment of inertia about, of course, a specific choice, and the angular velocity omega z k hat. Okay. Now, if you look at the parallels between this and translational momentum, the translational momentum, of course, not necessary about any point because it's a property of the system at a given instant of time. That L that we got in the morning was nothing but mass times the velocity. Okay. Instead of mass, we now have the moment of inertia. So in rotation, the role played by mass in translation is played by the moment of inertia. So is that important. Okay, you know how important mass is in most of our physics problems. As important when you come to rotations rather than translations is this quantity, the mass moment of inertia, because it plays exactly same role that the mass plays, and therefore its significance. Instead of the translational velocity, we now have the angular velocity. Instead of the translational momentum, we have the angular momentum. Okay, so just look at the parallel between them, and of course this is the definition for your IZZC, and very easily you can look at the other things, like when it is ZZ over here, you do not have Z's over here, you have the other two, which is X and Y. Okay, when you want YY, it will be X and Z over here, and so on and so forth. Okay, so there will be three such products of three such moments of inertia, XX, YY and ZZ, and in fact this can be thought of as a 3x3 matrix in which the principal diagonal elements are IXX, IYY, IZZ, all about C, and then of course you have the products of inertia, XY in the first row, second column, XZ, and so on and so forth, right? So it's populating that entire matrix, because you have two subscripts, is essentially can populate a square matrix with each of those subscripts running between X, Y, and Z. Okay, when they are common, it's a principal diagonal. When they are not, it's an off diagonal term. When it's same, we call it a moment of inertia. When it is different, we call it a product of inertia. That's the difference. Okay, so these are things that you have known before, but not in such a formal sense and in such a holistic sense where you see where each one of these things is going and where it is coming from, which is the bigger picture that is important for you to understand. Then you'll understand all of these from a very, very different perspective, and it becomes much easier to employ them in specific problems. Okay, so IZZC, as I said, is the rigid body's moment of inertia about the z-axis and passing through C, because the z-axis can pass through many different points. Like for example, in this room, it being a cuboidal kind of a shape, pretty much, yeah, I can say along the length I have X, along the width I have Y, and along the height I have Z, right? So now if I have this, that K hat, I can put it either at this corner, I can put it at that corner, I can put it somewhere in the middle, doesn't matter, right? But it has to be vertical. That's all that matters. Okay, so essentially it's not enough to say it's about the z-axis. It's not enough to just put the subscript ZZ. I have to have the superscript Z to say where that vertical axis I'm putting, and that's through the center of mass. Only then this particular, whatever we have said in this slide, is valid. Okay.
So is XC and YC the coordinates of where the center of mass is?
Exactly.
And then if you were doing this for a 2D problem, looking for the moment of inertia, you mentioned for a 3D problem you can convert dm to rho dv.
Yeah.
For a 2D problem, what would it be?
It would be the same thing, just that dv will then break into an a dx. It will break into. Yeah, so it will break into whatever is the thickness. Let's say, see, it's essentially like, let's say this tabletop. Okay, so it's a constant thickness throughout. So I can take it as T dA. My dV, I can take it as the thickness T times dA. Okay, so instead of a volume integral, it becomes an area integral. Okay, or you can put it the other way around. Your rho, which we had taken as mass per unit volume, I can now take it as mass per unit area. Okay, so different. It's called an areal density instead of a volumetric density. Yeah. So, any other questions, doubts about this? Okay, good. let's continue. The Euler's second law for 2D rigid bodies, which is just what we introduced. Now we want to get it in terms of quantities that we already know, which we have introduced before, namely your angle theta of rotation, the angular velocity omega, which is nothing but theta dot, because it's 2D, remember, that we are looking at. So omega can be written just as theta dot. Okay, and your alpha can be just written as theta double dot, right? So you have theta double dot and theta double dot, the angular rotation, the angular velocity, and the angular acceleration, and we can put the same Euler's second law in terms of this for a 2D rigid body, which is what we will do in this slide. Okay. Now for 2D rigid bodies, as we saw in the previous slide, for all rigid bodies, we know that the moment about the center of mass is equal to the time rate of change of the angular momentum about the center of mass. But for 2D rigid bodies, once it's two-dimensional, with the expression for your hc, that is the angular momentum about the center of mass, got simplified to this particular expression, which is Izzc omega z times k hat, as we saw in the previous slide. So we're just substituting that quantity within the brackets for your hc. It's an hc dot equal to mc is something we had derived earlier slide, and just the previous slide, immediately previous slide, we had also derived hc equal to this. So we are combining these two results over here. So the only xy planar forces are there. There is no force along the z direction. That's the characteristic of your 2D motion, that there will be only moment about the z direction. There will be no forces in the z direction. All forces will be in the xy plane. So that's by definition of a 2D problem. Okay. So when you have such a 2D rigid body problem, then you have, because the forces are only in the x and y directions, the moment will have only z components. Okay. So that z component means that you will have the scalar equation that you are having over here, that is your mc, even though it's a general vector over here, now I'm only interested in the z component of that. Okay. You can already see that there's only a k hat over here, right? So you're only interested in a z component of that, and that is, so now I can take out, it essentially becomes a scalar equation, right? So I don't need to deal with vectors anymore, because there's only one rotation, one direction of rotation that is involved, which is about the k hat or z direction, and therefore I can deal with just those. And it's very similar to what we were doing with in translation. We were dealing with what is known as rectilinear motion, motion along a straight line, or for that matter, motion along a curved path. We introduced a concept of S, and then we could deal with just scalar quantities. We didn't need vector quantities over there. So something very similar to that over here is happening as far as rotation is concerned. And just like we were dealing with the mass being either constant or not, in most transport vehicles we said it's constant, and therefore we could, I mean it's not constant, but still for a small phase of the flight we could probably take it out. So same thing, similar. Whatever holds for the mass, similar kinds of things holds for the moment of inertia. So for all practical purposes, for certain small phases of flight, I can take my Izz out, which is what we have done over here. So this is a more reliable equation, this one, whereas this is a little more cruder approximation, because we are not taking into account how Izz changes with time. We're only taking how the angular velocity changes with respect to time. It's okay for a small maneuver which lasts for a few seconds or a minute. Okay, now coming to which doesn't have much of a fuel burn. So now we look at this, what am I doing over here? Yeah, just replacing the d by dt's by dots. Okay, so instead of a d by dt, I'm just putting it as a dot over omega, and of course omega in turn is nothing but theta dot. Okay, because it's a simple 2D problem. In fact, you've been doing that for a lot of your homework questions as well today. So omega dot, omega itself is theta dot, now it's omega dot, so it becomes a theta double dot, which is nothing but acceleration, angular acceleration, which we denote by alpha. Okay, of course all of these are about the z direction, because it's understood that rotation is happening only about k hat. Therefore we can drop off without loss of generality the z's, and I can just call it as omega dot theta double dot alpha. It's understood that it's only the z component we are dealing with, and we are dealing with only scalar quantities in a scalar equation. Whereas translation still remains a vector equation because it's along both x and y. Even for a 2D rigid body motion, it continues to require vectors in general. It's only for the rotation that we can simplify this. In the case of the aircraft, it's just for the pitching motion that you can typically write everything in as a scalar equation, whereas for the forward and vertical, it still is a vertical, is still a 2D problem in which vectors are required. You cannot go with scalars. Okay, 2D rigid bodies, you have the rotational dynamics, which implies is a scalar equation, and whereas the translational dynamics is 2D vector equations, exactly what I said just a few seconds back. Okay, now we go back to 3D. Okay, so we are just going back and forth between 2D and 3D to see what is the simplicity in 2D, what is the general form of it in 3D, so that you understand both from the same perspective. Okay, so now we're talking of the angular momentum of 3D rigid bodies. Now instead of those specific choices that we had, remember what were the specific choices which were very simplifying in nature for our derivations? One is the choice of center of mass, the other is an inertially fixed point. The center of mass we denoted by C, the inertially fixed point we denoted by O. Now we talk of a generic point P, which need not be either O or C, okay? Some arbitrary point P that we want to take, which is a part of that rigid body, okay? So in that case, we will see that this is the final expression that we are going to end up with. This we are familiar with, the second term, which is having two R's and omega sandwiched between them. So that's something that was there for even the simplest case. But now once P is neither C nor O, for that general case, you will have additional term, which was dropping off for us when P became C or O. That doesn't drop any longer, and therefore it continues to remain. Very easy to specialize this and see. When your P becomes C, you see that the first term is RCC. So it's the position vector from C to C, which is from the same point to the same point, which essentially means that is 0. Okay, so you can see that. On the other hand, if it is O, why would this go to 0? If instead of P being C, then you can see very clearly this itself goes to 0. What if P becomes O? Why does that term drop off?
What is the origin of inertial frame of reference? So, OC particularly is the RC only.
I'm sorry, this should be not small p, but this is also uppercase P, okay? Which means the velocity of that point P.
If P was fixed under inertial frame of reference, then wouldn't PT be 0?
Exactly. So the first case, this goes to 0, second case, this goes to 0. Don't even need to go for the cross product and say parallel, etc., etc. In one case, if it's the center of mass, the first term goes to 0, otherwise the second term goes to 0, and because of which the cross product goes to 0, right? So now let's just walk through this derivation, and you see that you consider the point P, it's in any point of the rigid body, then you have the angular momentum about that point is nothing but, by definition, it is the moment of the translational momentum, and the translational momentum is VQ dm, integrated of course over the entire body. This is an infinitesimal mass, and this is the center of that infinitesimal mass we are calling as Q. Velocity of that we are calling it as VQ, again with respect to an inertial frame of reference. So superscript I is default. Now that is just this alone, when integrated, will give you translational momentum. But if it is crossed with RPQ and then the integration is taken, then you have, instead of translational momentum, you have angular momentum, but you can't say just angular momentum of the body. You have to say angular momentum of the body about this point P, okay, which is what we are putting over there. So where Q is a point in dm of RB, the rigid body, as we already mentioned. So these are standards that we are using, P, Q, O, and C. We are keeping it consistent in all the derivations in terms of their meanings. Now we're talking of the velocity at any point in terms of velocity at any other point, as long as those 2 points are fixed in the rigid body, a formula that you're very, very familiar with in a general case, right? So just that we are giving some specific meanings to Q and P over here, whereas it is valid for any Q and P which are fixed on the rigid body. And in our case also, this Q is the material point which is fixed on the body, and this point P is also some other point which is fixed on the body. So we have both of these satisfying the condition that they are fixed on the body, and therefore this formula is valid, where omega is the angular velocity of that rigid body on which P and Q are fixed, and this is the position vector from one of them to the other. Okay, so now all that we have to do is to substitute for VQ over here using this general formula that you have. So now you're going to have two terms. Once again, you're going to have an RQP cross VP, from which you get this, and the other term from which you get this. I think it's fairly straightforward. We've not changed anything over there, right? So yeah, we have changed, yeah. So you look at the first term, we have taken the advantage of integral of RPQ dm to be nothing but RPC, okay? Because that's the definition of your center of mass, okay? So we have taken that, so that's why this has come out, and therefore there's no longer an integral over there, and VP has come out. So VP is not changing with from point to point, it's of a particular point on the rigid body. So that has come out of the integration. All that you had is an integral of RPQ with dm. RPQ with dm is nothing but RPC by the definition of the center of mass, and therefore that is what you have there. Whereas the second term, we are retaining it as it is, just taking the RPQ cross into this bracket and putting omega cross RPQ as it is. We are not able to simplify this any further without further information, right? So this is the only new term that we are having, and having this complicates matters in terms of overall derivations, which is why we typically prefer to choose P either as C, in which case this goes to 0, or as O, in which case this goes to 0, and therefore we are left only with this integral term, not with that first term over there. Okay, now we want to move further, continuing with 3D rigid bodies. But now we want to look at, instead of a point fixed on the body, which is what we did last slide, we are going to talk about an inertially fixed point of the rigid body, okay? So inertially fixed point of the rigid body essentially means that there could be an axis of rotation, for example, on which the points are coinciding between the inertial frame and the rigid body, okay? So that's an example of that, but there could be other examples as well. It could be just a pivot point instead of an axis of rotation, for example, okay? So in this case also you will end up with the same simple formula that you had for center of mass, you will have for such points as well, that you will just have this integration of the double cross product term. Yeah. Now you recollect that this is the general expression we had at the end of last slide, where we said that the angular momentum about any arbitrary point P which is fixed on the rigid body is this. Now we just want to specialize this for P being the inertially fixed point, which is again something that Daniel already pointed out, that Vp will then become become 0 because it's fixed, and therefore it's 0, right? V is 0. So point fixed in both the rigid body and the inertial frame of reference means that IVP equal to 0, which means the first term drops off. It's what is known as the pivot point, the point about which it could be like a hinge, for example. So it's essentially a pivot point in 3 dimensions. Of course, we have dealt with pivot points in 2D, where it becomes a loci of pivot points, and therefore it becomes the axis of rotation, okay? So I would rather call this loci of pivot points becoming the fixed axis of the rotation in the 2D case, whereas in 3D case it's just a single point that we are talking about. Okay, now same thing in a simpler version. So far we looked at 3D, we're now looking at 2D. Things become a little simpler because now we can introduce that concept of the mass moment of inertia that we already introduced. We can take advantage of that. So once again, it's the angular momentum expression for a 2D rigid body about any point, okay? No conditions whatsoever. So P is an any point, which is arbitrary point. So obviously we'll have both those terms. One is the integral term, the second term, and the non-integral term, which is the first term. Both will remain, but one of them will get simplified, namely the integral term, because most things come out of the integral, and only whatever is there can be simplified and called as the mass moment of inertia about the z-axis, about passing through P, which is what we have as an expression. Then instead of that integral term that we had, r cross omega cross r, we just write it as simple as this, okay? But this complexity remains because we are giving the freedom of about any point. Okay, so recollect that we had this generic expression for any point P. I think in all these slides I have to change this lowercase p to uppercase p, some of that is scripted, okay? So for any point P of the 2D rigid body, as before, we have the position vector only in the xy plane and the angular velocity only about the z direction. So same thing as before, and that is what results in these equations. So your IZZP, of course, once again is the moment of inertia of the rigid body about the z-axis, which is why we give a subscript zz, and it's passing, that z-axis is passing through the point P, which is why we have this superscript P over there, okay? And which is why, of course, in the definition also you will have that P, point P over there, not any other point in general, okay? So AM expression, that is the angular momentum's expression, once again for 2D rigid bodies, but now instead of any point, we are saying any fixed point of RB. That is on the rigid body, this is a fixed point, then what happens, okay? So it's the same thing we are doing for some special cases so that we can use the special equations as and when they are applicable for a particular problem, okay? You can always go back to the general formula and derive from that, no harm, but once you know these specialized cases, you can start from there, reducing the number of steps for you in terms of your calculations. That's all. Otherwise, there's no big deal that we are doing in each one of these slides. It's just that the choice of points, the choice of the axis, whether it is 3D or 2D, these are the kinds of things that we are making. And in terms of the choice of points, it could be center of mass, it could be the inertially fixed point, a point fixed on the rigid body, a point, any arbitrary point, etc. And for each of them, we are coming up with the expressions, okay? So for rotation of 2D rigid body about the fixed axis, which is now PQ, because Q is the arbitrary point and P is that point about which we are taking these moment and the angular momentum. So HP just becomes, as we did in the previous slide, just IZZP omega zk hat, because it's 2D, because everything which is rotational in nature, be it the rotation vector or the angular velocity, angular acceleration, angular momentum, everything is along the k hat direction, and that's what we have over there for the expression for HP as well. And of course, IZZP is now defined in this way. So now there are some tricks of the trade. We don't need to always reinvent the wheel, do things which people have done already. So one thing that we take advantage of is those tables that I said, which are given in books for centers of mass, which we discussed in the morning. Similarly, for I also, expressions are already given in those tables, same tables, in fact, which gives the center of mass of various standard shaped bodies like sphere, cylinder, cone, prism, etc. You will have in such a situation the I values, the IZZ that we've been talking about, that will also be given. And when you have something like that, you can take advantage of that. So Euler's equation about a fixed axis, that is the pivot point, and for those of you who like to refer to your text, it's in 4.4 and 4.6 sections. So the parallel axis theorem, okay, again, this is something you might be familiar from other courses, we'll quickly rush through this. So essentially, you know about a particular axis. Can you get it about another axis which is parallel to the first axis if you knew the distance between them? That's all that we are going to do. So we'll introduce that notation for the distance between those two axes which are parallel to each other. We will call that distance as d, small d, lowercase. So that's the distance between two lines which are parallel to the z-axis, because we are considering a 2D problem, and therefore all the rotations are about z, and therefore any two z-axis that you have to consider obviously have to be parallel to your k hat, and obviously have a constant distance between them because they are parallel, right? So passing through both these points, P and C, P about which you are taking the moment, and C is the center of mass. Okay. Now, because it's a 2D problem, your D is entirely, of course, your general case of the Pythagorean theorem will be x squared plus y squared plus z squared. Here there's no z squared, only an x squared and y squared, and those x and y's are, of course, from going from P to C, which is essentially what you see over there, right? And of course it's squared, so the sign doesn't matter. So it's x squared plus y squared that you see over here. So it will also not matter if you interchange this going from P to C instead of C to P. It really doesn't matter because the signs will reverse, the squares will remain the same. So when you have this kind of a situation, then we see that there is a relationship between IZZ about an arbitrary point P and about this particular point, which is the center of mass, which has certain special features that we already know. And usually in the books, what will be tabulated will be your IZZ about C, about the center of mass. But in many examples, your axis of rotation might not be passing through the center of mass. It might be a distance d away from the center of mass, in which case what you will need is IZZP. But you don't need to calculate it from first principles by that integration. Remember, xp squared plus yp squared, and then integrate with dm or rho dv. Instead, we can just use this ICC and add a term, and that term that you need to add is just the total mass of the rigid body multiplied by that distance d squared. Okay, this is the parallel axis theorem, which also gives us an insight into one beautiful thing, that the minimum value of IZZ will be about C, because this will always be positive. Mass is always positive, d squared is always positive. So this is only going to get bigger than IC. Okay, IP will always be larger or than or equal to IC. So which means that the mass moment of inertia about the center of mass will always be the lowest that you can get. And therefore, sometimes you will see there's a huge advantage of passing your axis of rotation through the center of mass rather than through any other point. The amount of energy dissipated or work involved in carrying out a particular rotational motion will be much lesser, and that can be taken advantage of. Okay, so this is the parallel axis theorem, which we will typically use in many situations. In fact, you will be using it quite frequently in your next homework, I believe. Right, coming to the parallel axis theorem, we can now take that forward. What we had over here is essentially for this is a general thing that we had. Now we are going to specialize this for various situations. Like here, for example, you are looking at a set of particles that you have, Mi. So when you have a set of particles, what would be the similar situation? To find the moment, this is again a rigid body like the previous slide, but the rigid body is made out of some standard shapes, because the rigid body is having a complex shape, but you can think of it as a modular construction where it's made out of each module is a special shape, which you will find in tabulated values for MOI as well as the center of mass location. So once you have such a problem, it's just like how you are adding up the system of particles to get to a rigid body. You can add the set of parts of the rigid body of special shapes to get to the complex shaped rigid body. So to find the moment of inertia about the center of mass for a rigid body which is composed of multiple parts, all that you have to do is to take the mass of each one of those parts, then which is if there are n parts, each one of them m1, m2, mi all the way to mn, each of them at a certain distance from the actual center of mass of the overall body, which we don't know where exactly it could be. That's also something sometimes that you have to determine. And then your mass moment of inertia about the z-axis passing through C, the center of mass. And again, all of these we're talking about the ith part of the many parts that overall rigid body is made out of. Okay, so for the ith part we are talking of the mass moment of inertia. So this is also for the ith part, and m is also for the ith part. So given the mass, location, and moment of inertia for each and every part that the overall rigid body is composed of, about its own center of mass, that is the center of mass Ci rather than C. C is for the whole rigid body, Ci is for each part of that rigid body, center of mass. So similarly, the moment of inertia of each part about the rigid body's center of mass can be derived using what we just introduced in the previous slide, namely the parallel axis theorem. Because we know it about its center of mass, that is the part's center of mass, Ci,